So remember, the big takeaway is that SOHCAHTOA, that right triangle definition of sine, cosine, and tangent, requires, shockingly, a right triangle. If we don't have a right triangle, we need to use something different. So that those something different are going to be the law of sines and law of cosines. So we're going to start here by deriving the law of sines. So when we do these derivations, are these something I expect for you to be able to reproduce?
No.
No, right? I want you to be able to follow the argument as to see where these formulas are coming from, but they're not necessarily something I'd expect you to reproduce on your own. Okay? So let's say we have some non-right triangle. Let's call it, or name the vertices A, B, and C. Now, an important point, regardless of the derivation or not, and going to be a super critical thing that you're able to remember for the formulas in this chapter to work out for you, is the way that we name the side lengths of a triangle. So if I have a triangle with vertices A, B, and C, I'm going to name the side lengths of this triangle in a very specific way. So we use the capital letters for the vertices, and we're going to use the lowercase letter for the side length. Now, the question becomes, which location do I put, for example, the lowercase letter A? Yeah, I want it to be on the opposite side from the vertex. So location 2 is where we'd get the label of little a. Where would the little b go? So which number? 1. Okay. And then obviously then little c is going to go in the remaining spot. Everybody's okay there? All right. So if I'm going to deal with this non-right triangle, and how do I know it's not a right triangle, just for grins? I can look at this and know it's not a right triangle. How do I know that? Yeah, there's no right angle symbol in a corner anywhere, right? That's it. You know, that's kind of what you're saying.
I was talking about like how there was angle C.
Yeah. So what I'm going to do is I'm going to start by drawing in an altitude. So an altitude is a segment that goes from one vertex to the opposite side and intersects the opposite side at a right angle. The advantage of doing this is that it creates 2 right triangles for me. Everybody can kind of see that, right? And just for the sake of argument, let's call that altitude H. Everybody's okay with that? All right. So using the blue triangle, I can use SOHCAHTOA in there because it's a right triangle and say that sine A is equal to H over B. And inside of the green triangle, again, SOHCAHTOA applies because it's a right triangle. I can say sine B is equal to H over A. Everybody good with that? I'm now going to take these 2 equations. I notice each of the 2 equations contain the variable h. So I'm going to solve each of these equations equal to h and then set them equal to each other, because that's something we can do. Everybody so far so good? Okay. what I'll do now is I'm going to divide both sides by AB. So I'm left with sine A over A is equal to sine B over B. Everybody so far so good? Happy with this? Okay. If I go back to the beginning now and repeat the same process, drawing in a different altitude, I would get a different proportion, right? I get like sine B over B is equal to sine C over C. Everybody agree with that? But inside of that proportion, one of the two ratios is going to be the same, right? Regardless of which other altitude I draw in, I'd either have sine A over A in the proportion, or I'd either have sine B over B in the proportion. Everybody agree with that? So when I hook those two proportions together, I can say the final version which is our law of sines. I'm going to abbreviate law of sines as LOS. I'm going to write that probably 100 times this chapter, so I don't want to keep writing it over and over and over again. So I'm just going to abbreviate it. Everybody feel okay here? Oh, okay. Okay, so let's look at an example here. We're asked to solve the triangle where we have the angle A is 32 degrees, angle B is 73 degrees, and angle C is 13 degrees. First thing I'm going to do on a problem like this is to, I'm going to draw a picture to help kind of just give myself a visual sense of what's going on. So I'm going to call this guy angle A. I'm going to call this guy angle B. And I'm going to call that angle C. So which segment am I going to label C? Yeah, it's the segment AB, right? So that's my C, so I'll write 13 there. Which segment am I going to label A? CB. And which segment am I going to label B? AC. Everybody feel okay as how we pick those labels? Now it's important that you do that you're labeling the opposite side, the lowercase version of the vertex name, because these formulas don't work if you're not naming your triangles in that same fashion. Everybody understand? Okay. All right. So to solve this triangle, we need to get an answer for angle C, an answer for side A, and an answer for side B. Which one should we find first? Great, angle C. How are we going to find the value for angle C? Okay, good. So that's a geometry theorem that hopefully you remember called the Triangle Sum Theorem. It says that the sum of the interior angles in a triangle is 180 degrees. Just to tie this back to geometry a little bit. Since many of you probably remember using the law of sines or law of cosines in your geometry course. I assure you did, even if you forgot it. At least if you took the Notre Dame Prep geometry course. Some of us took geometry in middle school, probably. And I can't speak to what you did in your particular middle school. All right. That's good. Now what? Does it matter which one we solve for next? No. Okay, let's pick one, A or B. A, great. So if I go back and I use the law of sines, which two proportions am I going to use? I'm going to use A and C. Very good. Why did I pick those two? Because we know everything about C. We know the angle measure and the side length. And in A, we know the angle measure, but we don't know the side length. Everybody feel so far so good? So to solve this proportion, I'm going to cross multiply. And then divide. Everybody feel so far so good? That's all right? Now it's calculator time. What mode do I need to be in on my calculator? Yeah. Good. So 13 times sine 32 divided by sine 75. Check my mode real quick. I am in degree mode. So I get 713. So I'll write that, 713 inches. Feel okay there? All right. Now all that's left is to find side C. Can I use the Pythagorean theorem here? I know two of the side lengths. No, why not? Not a right triangle. Got to be careful about that. I would say that every year, multiple students make this mistake and start trying to use the Pythagorean theorem on non-right triangles. Got to be careful. Okay, what should I do instead then? Law of sines, okay? Which two ratios am I going to use in my law of sines? Doesn't matter. It matters a little bit. Which one definitely needs to be in there? B, right? Which other one would be the better one to choose, A or C? C. Why is C slightly better than A? There's no rounding, so you get a slightly more accurate answer. Now, if we're rounding to like 2 decimal places or something, it probably doesn't matter. But if you're trying to land a spaceship on the moon or something, that probably matters. So, since we don't know what we're using this law of sines to do, in case we're landing moon rockets, let's be careful here. All right, so we can say that sine of B over B is equal to sine of C over C. Cross multiply. And then we divide. And now it's calculator time. Notice that basically all I have to do is change just this one thing. So I'm just going to go back and edit. Did I make a mistake? There seems to be a lot of whispering going on. Is it all okay? Okay. I just checking, man. It's every time, it's Monday. I got like 3 hours of sleep last night, so I'm not functioning at 100% capacity here, but I mean,
we really didn't want to.
We kind of do, though. You guys pay a lot of good money to get a good education. I'm going to try to let you get your money's worth. I know, right? Huh? Okay. All right. To where? baby.
Sloan is five.
Was that the club?
Yeah. Yes, that was it. The Sunday night club scene is bumping. And if by club you mean trying to get a baby to fall asleep, then yes.
What's your baby's name?
Sloan.
How old is she?
Coming up on 5 months.
Wait, so when was she born? 5 months ago.
Yeah. Like 5 months ago.
Oh, wait, yeah.
The beginning of August.
Can you show us a picture?
I don't have a picture on my computer right now handy. Yes. Can somebody answer that? Like what I did before where I show you where the formula comes from. All right. So, by and large, Chapter 7 is very straightforward, and there's not a whole lot of tricky things going on here. This is the one tricky topic in Chapter 7. This is by far the hardest topic in Chapter 7. Because there is a certain situation in which a couple of different things could happen. So this is the ambiguous case is what we're talking about. So what I want you to do for a moment before we start talking about this is go back to your geometry class. Think back and think about the triangle congruence theorems. They're like 3-letter combinations. Does anybody remember any of the triangle congruence theorems? So there was side, angle, side, I heard somebody say. Yep. Side, side, side is another. Angle, angle, side is one.
Oh, side, angle, side.
We had that listed already. Angle, side, angle is another.
Angle, angle.
That wasn't a congruence theorem. That was a similarity theorem.
Side, side, angle.
Okay, so the last one, side, side, angle, is not a congruence theorem unless there's a special situation. So the side angle only works as a congruence theorem if you have a right triangle. If that angle is a right angle, then it's good. If it's non-right angle, it doesn't work.
Okay.
And the reason it doesn't work is you could end up with 2 different triangles. And that's the ambiguous case.
Yeah.
So each of these, you can have 1 triangle. Here you could have 2. SSA. Yeah. Okay. So let's look at this SSA situation. If I draw a triangle, here's my angle A. That's the angle that we're given. So you're given angle A. What 2 side lengths could you be given? So you could have AB and BC, or you could have AC and BC. So you could have these 2, or you could have those 2. You can't have the 2 arms of your angle A. Why not? That's side angle side. Everybody's okay with that?
Yes.
Okay. So the ambiguous case that you're worried about is only this SSA situation. Good with that? Okay. So the first case is that given angle is either greater than or equal to 90 degrees. It's either a right triangle or it's an obtuse triangle. Just for the sake of argument, I'm going to draw some triangle here, ABC. Okay, so if we have a right or obtuse triangle, so if A is 90 degrees or bigger, what does that make side BC? We have a special name for it. Side BC would be the, starts with an H, it's the hypotenuse, right? Because it's the side opposite the biggest angle in the triangle. So, can we have another side that's bigger than the hypotenuse? No, that's impossible. That's why you're getting 0 triangles. Can we have another side that's equal in length to the hypotenuse? No. That's why you have 0 triangles. Everybody's okay there? So the situation where you have a right triangle or an obtuse triangle, it's pretty easy. All you have to do is check to make sure the hypotenuse is actually the longest side. If it is, there's just one triangle possible, and you just do it the same way we did in the previous example. Nothing more to consider there. Okay, so that's not a big deal, right? Why am I doing that? Why not just do this? That makes life easier. So in the case where you have the given angle is acute, notice that I'm not going to call that an acute triangle, because just one angle that's acute doesn't necessarily mean you have an acute triangle, right? Everybody agree with that? Okay. So if I'm given an acute angle, and the side opposite that acute angle is at least as big as the other given side, one triangle. Nothing more to consider. The tricky situation is where the side opposite the acute angle is smaller than the other given side. This situation is what we call the ambiguous case, because on sight, you don't know whether you have 0, 1, or 2 triangles. So when we talk about the ambiguous case, that's the situation that we really need to worry about. The other ones, it's just one triangle, or it's a silly impossible situation where like the hypotenuse isn't the longest side. So let's talk about how can we tell, right? So eventually, we want to know which one of those 3 situations we're running into. Whether this is the 0 triangle situation, the 1 triangle situation, or the 2 triangle situation. So here's the easiest way to do that. I'm going to show you guys just with an example. So I'm going to just start by drawing a picture. Note that this triangle is not to scale. I don't even know if this triangle is really possible to draw, or if there's one of them or two of them or whatever, but it usually helps me to just kind of get a picture of what's going on. Everybody's okay with that? Okay. So notice here that my given angle is acute, and the opposite side is less than the other given side. So this is the ambiguous case, right? Because the opposite side is smaller than my other given side. Cool? So we know that this is the situation we have to be very careful with. So to figure out whether I'm looking for 0, 1, or 2 triangles, what I'm going to do is I'm just going to use the law of sines. So I can say sine 56 over 16 is equal to sine q over 19. So if I cross multiply and divide, I'm going to not show the cross multiplication as a separate step here. I hope everybody's okay with that. I get this. And this 0.984, this result, is what's going to tell me whether I have 0, 1, or 2 triangles. So that number at the end there, after we apply the law of sines, is going to tell me whether I should be looking for 1, 0, or 2. That was a weird way of saying it, triangles. So if that number at the end is less than 1, we're going to get 2 triangles out of that. If it's equal to exactly 1, we're going to have 1 triangle. And in fact, what kind of triangle is it going to be? It's going to be a right triangle. And if that number is greater than 1, or I'm sorry, yeah, if it's greater than 1, we have 0 triangles. That seems a little arbitrary, right? Like, why is that? Like, what's significant about 1 there, right? Why is 1 the breaking point for these 3 different situations? Well, if I wanted to go and solve for angle Q, I would take the sine inverse of both sides, right? Everybody agree with that? Okay. If I remember my all silly turtles crawl, sine is positive in the first and second quadrants, right? Both those angles are possible angles inside of a right triangle because they're both between 0 and 180. Everybody agree with that? Where is sine going to be equal to exactly 1? Right there at 90 degrees, right? So, there's that. So that would make Q would be at a 90-degree angle, a right angle. And if it's greater than 1, is sine ever greater than 1 on the unit circle? No. So if my value for sine Q is greater than 1, that's a bunch of hot garbage. That can't happen. There's no such angle that will do that, hence no triangle is possible. Does that help out a little bit? Okay. So let's go ahead and finish solving this now that we had this little aside. So if I go now and I calculate sine Q, yeah, of course. Of course. And I'm going to do a little bit of overkill here, and I'm going to type in, I just stole I didn't type in to get the 0.984. Sometimes the decimal points matter a little bit, depending on how much accuracy you're looking for. So I'm going to keep all my decimal points. So that's 79,893. So I'm going to try to keep 3 decimal points through most of this. Actually, I'm going to use all of the decimal points when I get it. Or when I put them in the calculator. I'm going to write down 3 of them, though. So that's one answer. How do I find the other answer? So this is, angle here is 79.983, right? So this angle over here that the terminal side makes with the x-axis is also 79.893. So how do I find the standard position angle? This one right here. Yes, 180 minus that answer. So 100.107. Should I copy that down right? Okay, good. Is everybody okay here? So I have 2 answers for Q, hence 2 triangles. So I'm going to reorganize my work now just to make things a little bit clearer. So for triangle 1 and triangle 2, in each of them, the given information is the same. Angle P is 56, side P is 16, and side Q is 19. But in the first triangle, angle Q is 79.893 degrees. And in the second triangle, angle Q is 100.107 degrees. Everybody so far so good? Did I name that third vertex? Oh good, I did call it R. Okay. So how would I find angle R then? Yeah, 180 minus angle P minus angle Q, right? So 180 minus 56 minus 79,983. So 44,107. And for the other one, 180 minus, was it minus 50? I said minus 56 minus, I'm yelling at the calculator, and then minus 101 or 100, 107. So 23,980 or 893. Everybody good with that? Now, how am I going to find side R? Law of sines, great. Which 2 ratios am I going to use? Good. Good, I'm going to use P and R. Could I have used Q and R? Yes. Why is P slightly better, though? Yeah, there's no rounding in P, right? They're both exact. Bye, T-Money. And like I promised here, I'm going to use all the decimal points. And it probably doesn't matter, but, you know, I like to be careful on these. Oftentimes, because the values are so big, 1343, 2. Oftentimes, especially with the inverses and the signs and stuff, like a little bit of difference can make a big difference. In particular, when doing the inverses, you know, the difference between the inverse of like 0.7 and the 0.75 or something is a lot of degrees. Like it'll be more than a full degree difference. So I like to be a little bit careful here with my rounding and not really do any rounding with the calculator to use all the full values. If I do the same thing then over here, sine 56 over 16 equals sine 23,893 over r. So I get r equals 16 sine 23,893 over sine 56. And that's 7187. So to just give you a little bit of a geometric picture of kind of what's going on. So 56, 16, 19. So this was triangle 1. Triangle 2. And if this is my acute angle, remember my angle Q was the one that we found duplicate versions of. So that's kind of what's going on there. From a geometric perspective, what those two triangles look like. This one, I guess, is okay. Of course. Is that far enough? Okay. Okay. We're stopping here anyways. I'm done at this point.